So we're going to now look at how certain properties of liquids, to begin with, mostly we're going to focus on liquids here. The properties of liquids, how are they influenced by forces, intermolecular forces of attraction? So one of the properties of a liquid is surface tension. Surface tension is the property of liquids to try to minimize their surface area. And I'll explain that in one of the next slides exactly what that means. So we're trying to, the molecules though, for some reason, they try to minimize their surface area. And you can see in this picture here, here's a astronaut or someone in a gravity-free environment, assuming an astronaut. In fact, this doesn't say in the book what exactly this guy is. I was just looking to see if I could see it. Anyway, the point is, these water molecules are all, they're not just laying out flat in a gravity environment. They're all pulling inward to try to minimize the surface area. So they're trying to bury as much molecules of water into the center as possible and minimize how much surface area is available. A sphere happens to be the most efficient way to do such a thing. And so the strength that it would take to break apart that sphere or add more molecules to the surface, that's what we refer to as surface tension. And so we'll note that on the surface of a liquid, there is sort of the top layer of molecules on the surface behave differently than the molecules that are inside or in the depths of that liquid. We can see that, like for instance, you take something like this paper clip. Here's a paper clip, and I'm going to make my dot a little bigger. Okay, so here's a paper clip. And if I were to, that paper clip, if it were below the surface, would not float anymore. It would just drop right to the bottom because it's more dense. It can, and it will sink to the bottom. However, you can float, if you're careful, you can float a paper clip on the surface of water because of the surface tension. The surface of the water behaves a lot more like a skin, and you have to break through or penetrate through that skin then to enter the interior of the water. And of course, if that were the case, this would no longer float. It would just drop straight to the bottom. So the behavior of the surface is clearly different than that of the interior. The interior wouldn't hold up this paper clip, but the skin, so-called skin, the surface layer, which has a tension, you have to be able to break through in order to do that. So why is this? Well, that's what we're going to talk about in the next slide. So looking at surface tension a little bit more closely, we can begin to understand why surface tension exists and what it really is. The simplest way is to look at this little diagram here, and you can see that there are the molecules of liquid that are at the surface have less interactions with its neighbors than those that are found in the center or interior of the liquid. And because of that, the molecules that have more interactions with the interior are more stable. It's a more energetically stable situation than those who are kind of left hanging without the extra anchors holding it together. So let's see the implications here then. So things that are less stable, as you may recall from your other chemistry experiences, want to become more stable. So they tend to adjust themselves to maximize their stability. Now, what the net result is that these surface ones want to maximize their interactions, I'll use this one, with the other molecules around it, and they want to add to it and see how many they can get. Well, there's then a strong driving force. These surface ones want to move into the the center, and that's why that's why that happens, and that's why you would get a spherical droplet when you are in that sort of lack of gravity situation. Now, if you have a little, if I draw, here's my faucet, you got water dripping, you'll notice water pretty much as it's dropping will minimize its surface area. And the reason for it is these molecules don't want to be on the surface, they want to be inside. So they're going to try to fit as many inside as they can and make a stable complex, more stable situation. That's what's happening. So that means then that these molecules won't want to have something penetrate into the surface, because that will cause the molecules to spread apart and increase the surface area, which isn't what they want. In fact, if you start putting other things in here, then you're breaking other interactions with adjacent molecules, and that just is something that is not well tolerated. So we can measure surface tension in terms of the energy it takes to, say, move one of the molecules from the interior into the surface to increase the surface. That would take energy, and it takes energy because all of the intermolecular forces of attraction that are holding this interior molecule in place would have to be broken, and it would have to then move up and force its way into the surface. And so it would be going from a place that's more stable into a place that's less stable. So that's why it takes energy. And that's going to lead to, it's going to take energy to do that. So the energy it would take to increase this surface area is called the surface tension. And we can measure that then by looking at how much energy that is. In this case, we have 72.8 millijoules. Remember, a joule is a measure of energy. Milli is 1/1000th of a joule, divided by the area in square meters. So this says that it would take this many millijoules to increase the surface area by 1 square meter. That's what that's saying. So the stronger the interactions that are holding the molecules together, the larger that number becomes. Because if there's stronger interactions holding the molecules together, then it would take more energy to break them apart and force them into the surface. And we can compare that to benzene, for instance. Benzene is a non-polar molecule, so that means induced dipole interactions. Dispersion forces are what hold it together, and it takes a lot less energy to increase the surface area than it does for water, which is all held together by very strong hydrogen bonds. So because this has stronger forces of attraction holding it together, it has the higher surface tension. And in fact, if you were to compare benzene with water, in that first example I gave where a paper clip could be floated on water, that would never happen with benzene. The surface tension isn't strong enough to resist the penetration by the paper clip. Water is, benzene is not. And so you can tell they have different intermolecular forces of attraction that are holding them together, and so it's easier to break them apart. So the major factors then that influence surface tension, well, they're going to be things like how strong the intermolecular forces of attraction are and the temperature. Now, we already talked about how temperature can help molecules. If you increase the temperature, you increase the kinetic energy of the molecules, and that can give them enough energy to break free of the intermolecular forces of attraction that are holding them together. So if you have really strong intermolecular forces of attraction, it would take a lot more temperature to break those than if you had weaker forces of attraction. But in general, when you raise the temperature of a liquid, it will reduce its surface tension because you're giving the molecules enough energy to break free of the of the intermolecular attractive forces holding them together. And we'll see that that's why we mentioned kinetic molecular theory in the past. The kinetic molecular theory can help us understand how these properties behave. Strong intermolecular forces of attraction will increase the value of the surface tension. Temperature, because it opposes these intermolecular forces of attraction, will lower the surface temperature. Surface tension, my bad, surface tension. So viscosity is kind of like, it has similar kind of thinking as surface tension. Surface tension is the resistance of increasing the surface area, whereas viscosity is the resistance to a liquid's flow. And in order, if you think about it, in order for a liquid to flow, let's just kind of draw these. Let's say we have these molecules here, okay? And then we have another set of molecules, and so this is maybe they're interacting in a liquid. Well, in order for flow to happen, these molecules have to break free from the interactions holding them together, and then make a new interaction, and then make a new one and break free, and make a new one and break free. And so if these interactions, because they have to flow over each other, see? And if these interactions are too sticky, they have a high attractive force, then it's going to be a lot harder for these things to move and flow. And so we can measure that. There's a centipoise. A poise is a measure of that resistance to flow. Centipoise would be 1/100th of a poise, whatever that is, you know. But the point is, we can use that to measure viscosity. And so, first of all, the strength of the attractive forces, as they increase, viscosity increases, because you have to, it's going to be a lot harder for these things to flow and break free of each other when the force of the intermolecular force of attraction is much higher. So we can see this really nicely. You have all these hydrocarbons here, and the only difference is chain length. We go higher, 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 higher. We also have increased molar masses, and so the two things together, the longer chain lengths and the molar mass increase, both of those things increase the forces of attraction. So in this case, we're dealing with dispersion forces, induced dipole forces. That's what this is. So I'll write that out. So these interact with each other through induced dipole interactions. And so they induce the dipole on each other. And the things that increase the strength of the induced dipole are things like more electrons, more polarizability, and that is, we can see that that is the case when you increase the molar mass, you increase the polarizability of the molecule because there's more electrons that can be shifted around. The other thing is we're increasing the chain lengths in each of these cases, which increases the points of contact that these things can have with each other. There's more things interacting in these long chain lengths. So those two things together, you can see how as you increase the chain length, you increase the viscosity because you're increasing the strength of the attractions that are holding these together. This more or less reviews what we just said. The stronger the intermolecular attractive force, the higher the viscosity will be. And then if we were to look, say, up, compare these types of things here. So we got those long chains versus, let's say you have a bunch of, a carbon that's, you have something that maybe looks like this. CH3, 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 CH3. Okay, that has 5 carbons, so does this. And if we were to compare N-pentane, and I think I showed you this before, but anyway, this has fewer points of contact, this circular sort of spherical depiction, and so it will actually have less forces of attraction holding this together than the pentane would have holding itself together. And so this would have less viscosity than this. This would have more viscosity. Raising the temperature also can reduce viscosity, and that has to do with the kinetic molecular theory again. You have more molecular movement. The molecules are moving around. They have more energy to break free of the intermolecular forces of attraction holding them together. And so as you increase, this is showing this here, as you increase the temperature, you increase the kinetic energy, and that decreases the viscosity because there's more energy to break free of the interactions holding them together. As a little an aside, I want to give you the following challenge. I want you to think about this and be able to explain it. Perhaps you have heard of this idiom. It's slower than molasses in January. I would like you to be able to explain this using kinetic molecular theory. What does this mean in terms of kinetic molecular theory? Let me show you what molecules you would find in molasses. First is you'd find mostly sucrose, that's table sugar. Note all of the OH groups that you would see. Okay. Then another sugar you'll find is glucose. And there's one more major sugar you'll find. And that sugar is fructose. And what I hope you noticed is there's a lot of OH groups around there. So what I want you to do is be able to, using the kinetic molecular theory, which is combining intermolecular forces of attraction with the kinetic energy, and explain why molasses is slower in January. So the next thing I want to kind of focus on is something called capillary action. We're familiar with capillary action. It's the ability of a liquid to flow up a thin tube against the influence of gravity. And if you have the tube is much narrower, you'll see the liquid rise to a much higher level. And it's really about two forces that are working together. We have cohesive forces. The cohesive forces are the forces that hold the liquid molecules together. And then there's adhesive forces. This is the forces of the liquid molecules to the tube's surface. So if it's a glass tube, it would be, you would be looking at the force of the water. Let's say water in a glass tube. Then you would have the cohesive forces are the forces holding the water together. The adhesive forces are the forces that help the water to interact with the glass. So the adhesive forces and cohesive forces kind of work together to essentially pull up the liquid into the tube. So let's look at that a little more. So here's some examples. Okay, we have a couple of examples, and we've all seen this. You've all used this maybe in one way, shape, or form or another. But you put in, here's two capillary tubes, each one a little different. This one has a bigger diameter than this one. This one has a bigger inner diameter than this one. So this one has the smaller diameter, and for some reason, the liquid flows up to a higher level than, say, when the diameter is larger. And then if you tilt it a little bit more, you can actually even get, sometimes have it go up a little higher. And now we can explain that using adhesive forces and cohesive forces. So if there is a good adhesive force, a positive adhesive force between the liquid and the tube, then the liquid is going to want to maximize its interaction with that tube because it likes sticking to it. So it's going to pull itself up. But if it pulls itself up, along with it becomes the liquid, because the liquid is also attached to each other. So as the liquid tries to creep up the walls of the capillary tube, the water, in this case water, but the liquid, because the molecules are also attached to each other, pulls them up along with it. And so that's how capillary action works. And if you tilt this to the side, well, then you're making it a little easier for the liquid to flow up, because it's not all the molecules are working 100% against gravity. So that's kind of the idea. So the molecules are attracted to the walls of the tube, and as they move up, they're bringing the other molecules that are attracted to each other and those liquids that are attracted to the tubes, and they cause the whole thing to move up. So it's the combination of both of those things. Very similar to capillary action is the formation of a meniscus. And you have, if you've worked in a lab, which most of you have already, and you've had to use a graduated cylinder, and you had to worry about a meniscus and how to read. So this is showing two different liquids in glass. We have water in a glass, and water actually rather likes glass. Mercury, on the other hand, doesn't like glass as much as it likes itself. Water likes glass a little better than it likes itself. So in this case, the forces of adhesion are greater than the forces of cohesion, and that leads to a meniscus that is pointing downward. It's concave. The mercury likes itself more than it likes the glass, so it's going to try to stick with itself rather than stick to the glass, and so you get a convex meniscus. So you can get either, and it just depends on what's higher, the forces of cohesion versus the forces of adhesion. So water forces of adhesion are greater than the forces of cohesion. So I'll just say adhesion is greater than cohesion, and in this case, adhesion is less than cohesion. And so you can kind of do that comparison. That's just an application of these intermolecular forces of attraction, either between more molecules of itself or between itself and some other foreign substance like the glass or plastic that you would find in a tube.